Good morning everyone. I am Muskan from BSc Chemistry Honors 3rd year and today I am discussing the electronic spectra of Pradeep's Physical Chemistry Volume 3. Electronic spectra. It has been discussed in the last chapter that when molecules absorb energy in the microwave region, transitions between the rotational levels takes place, giving rotational spectra. Similarly, if the energy is absorbed in the near infrared region, transition takes place between the vibrational levels accompanied by those in the rotational levels, giving vibrational rotational spectrum. However, if the light is absorbed in the visible region or ultraviolet region, electronic transitions takes place, giving electronic spectra. A number of other processes also takes place on absorption of light called photoprocesses. These may be photophysical processes such as fluorescence and phosphorescence or photochemical reactions. The branch of science dealing with such processes is known as photochemistry. In the present chapter, we shall take up a brief study of electronic spectra, whereas photochemistry will be discussed in the next. Electronic transitions and band spectra. Theory of electronic band spectra. Just as there are electronic energy levels in an atom, there are electronic energy levels in a molecules also. However, there are no simple formula available for the energies of these electronic levels except for the hydrogen-like atoms. Electronic spectra are obtained when the electrons in a molecule are excited from a lower electronic energy level to a higher level. However, as the electronic transition is accompanied by vibrational and rotational transitions, the total energy of molecule in any state is the sum of electronic energy, vibrational energy and rotational energy. If V and ER represent the electronic energy, vibrational energy and rotational energy respectively of the molecule in the initial state before transition, and E dash, E mu dash, ER dash the corresponding values in the final state, then we have the energy of the molecule in the initial state. E is equal to E plus E mu plus ER, and energy of the molecule in the final state, E is equal to E dash plus EV dash plus ER dash. Energy change involved in the electronic transition will be given by delta E equals to E dash minus E, that is delta E plus delta E mu plus delta ER. But according to Planck's quantum theory, delta E equals to h nu is equal to hc mu bar, or mu bar equals to delta E plus delta E mu plus delta ER divided by hc. As for a particular electronic transition, so that delta remains constant, and for a particular vibrational transition, delta ER can have different values due to different rotational transitions within the same vibrational energy change of same electronic energy level. A number of closely spaced lines are obtained. This constitutes a band. For each vibrational transition, separate band will be obtained. Thus, due to different vibrational transitions for a particular electronic transition, a set of bands is obtained called the band group or band system. Each electronic transition will give a band system, and hence the complete electronic spectra involving different electronic transitions give rise to a series of band groups. Thus, the electronic band spectrum obtained for a gaseous molecule is quite complex. In spite of the complex nature of electronic band spectra, these are preferred over the other types because these are obtained in the visible and ultraviolet regions, so that these can be easily photographed. The explanation: potential energy curves and Frank-Condon principle. The explanation of electronic band spectra and dissociation energy can be early understood in the terms of potential energy curve and Frank-Condon principle. The potential energy curve of diatomic molecule is obtained by plotting the potential energy of system versus internuclear distance between the two approaching atoms. The curve obtained is of the shape shown in the figure. However, even at the minimum energy position represented by point x, the atoms are vibrating. The vibrational levels thus occupied by the system may be represented by horizontal lines and indicated by appropriate vibrational quantum numbers. If the sufficient energy is supplied so that the system occupies the vibrational levels represented by the Vd, and the corresponding internuclear distance should become infinity, such that the molecules should dissociate into atoms. However, this does not happen because this stage is reached. The electron jumps to the higher energy level. electronic transition takes place and the dissociation will take place only of the molecule. Now, every electronic state has its own potential energy curve. They differ in the fact that the minimum of the potential curve for excited state second is at a large internuclear distance than the ground state. The dissociation energies for the two states are different as shown in the figure. This is evidently due to the fact that the bonding is weaker than in the ground state. The vertical distance between the minima of two curves gives the difference between the electronic energy. The transition between the two electronic states takes place according to the principle nuclei being much more massive than electrons, and electronic transition takes place much more faster than the nuclei can oscillate to change their internuclear distance. And electronic transition takes place from an extreme end of a vibrational level, example from A or A dash, because the velocity of the atoms is zero at these positions and they spend maximum time at these points. As internuclear separation remains the same, the transition can be represented by a vertical line from point A dash to a point C of the upper curve. The new vibrational level must be one which is nearest to point C. Counting levels, it appears that excited molecule will be in the third or fourth vibrational level of state second. This explains why in the electronic transition there is no simple selection rule for the transition among the vibrational levels. All the type of transitions from lowest vibrational level to any of the vibrational level of higher electronic state. It may be mentioned here that according to quantum mechanics, the transition from lowest level takes place from the midpoint of vibrational level, not from the extreme positions. Each vibrational level has a large number of very closely spaced rotational levels which have not been shown in the diagram. Now, when the transition takes place from vibrational level of lower electronic state to some vibrational level of upper electronic state, it is accompanied by a number of transition between the rotational levels. The result is a group of closely spaced lines called a band. Since a number of vibrational transitions takes place, a group of bands called the band system is obtained. Further, as the transitions takes place between many different electronic states, the result is electronic band spectrum consists of several band system. If electronic transition similar to A-C take place, the result is an absorption spectrum consisting of a number of the vibrational bands. If, however, a transition similar to BD takes place, where BD point represent the vibrational level corresponding to which internuclear distance is infinity, the molecule dissociates. Thus, when such a transition takes place, the absorption spectrum consists of a number of bands corresponding to transitions from the ground state to definite vibrational level in the upper state, but these bands will converge. Lastly, it may be pointed out that if minimum of the upper electronic state is nearly at the same internuclear distance of the ground state, and of the upper state is the strongest. Selection rules for electronic transitions in molecules. In order to understand the selection rules, we should first understand a few terms. Parity. Parity represents the behavior of an orbital with respect to inversion. It is used for the molecular orbitals of homonuclear diatomic molecules. We consider a point in the molecular orbital and note the sign of the orbital, then we travel equal distance through the center of molecule to a point on the other side. This operation is called inversion. If at this point the orbital has same sign, it is said to even parity and is denoted by Z, and if it has opposite sign, then it is said to have odd parity and denoted by U. The parity designations apply only to homonuclear diatomic molecules because heteronuclear diatomic molecules do not have center of inversion, as shown in this figure. Now the term symbol of the molecules. These symbols give the complete information about the state of the molecule, such as orbital angular momentum, multiplicity. Depending upon the component of total angular momentum about internuclear axis, they are given these symbols. To these above symbols, multiplicity is added on the left as a subscript and parity is added as a subscript on the right. The single electron in H2 positive in sigma molecular orbital has zero orbital angular momentum. Hence, the term symbol is sigma, and further it has the multiplicity too. The term symbol for any closed cell homonuclear molecule is 1 sigma Z because the spin is 0. And if there is only one pi electron outside a closed cell, its orbital angular momentum about internuclear axis is 1 unit. Hence, the term symbol is pi. And if there are 2 pi electrons, the term symbol may be sigma or pi, and the term symbol sigma will be used if the electrons are orbiting in opposite directions if they occupy the different orbitals. And in case of O2 in the ground state, the 2 pi electrons occupy the different orbitals with parallel spin, and overall parity of the molecule is G. Hence the term symbol is 3 sigma Z. Lastly, a subscript plus or minus on a sigma term is added to show the behavior of molecular wave function or reflection in a plane containing the nuclei. In case of O2, one electron is in 2 pi x, which changes the sign on reflection in YZ plane, and other is in 2 pi. Now we will given below the selection rule for transition between the different states of the molecules. Molecular orbitals that are involved in the electronic transition. The most common molecular orbital present in a molecule are the bond molecular orbitals sigma and pi, and the corresponding anti-bonding molecular sigma star and pi star. Besides these, there may be heteroatoms such as nitrogen, oxygen present in the molecule, which have orbitals containing the lone pair of electrons. As there are non-bonding orbitals, they are designated as n-orbitals, and they do not have any corresponding anti-bonding orbitals. In the case of HOMO, such as H2 and 2, the highest occupied molecular orbital in the ground state is a bonding, whereas the lowest unoccupied molecular orbital is an anti-bonding molecular orbital. The electronic transitions takes place on the absorption of suitable energy. This is the molecular orbital of carbonyl compounds and the transitions involved. The transition may take place from n orbital to anti-bonding molecular orbital. In other words, the electron may be excited from sigma pi or n orbital to sigma star and pi star. The transitions which are allowed are sigma to sigma star, pi to pi star, and n to pi star, n to sigma star. The type of transition involved depend upon the nature of the compound and takes place by absorption of frequencies characteristic of the compound. Taking the example of carbonyl compound, the sigma, pi and n orbitals and their excited states are shown in this figure. Further, it is interesting to point out that if a single electron excited from the lower orbital to excited antibonding molecular orbital has a spin opposite to that of the electron left in the lower orbital. If the two electrons in the upper and lower orbitals have the parallel spin, then their spin is equal to 1. So that 2s plus 1 equals to 3, the excited state is triplet. Thus excited state are classified as singlet or triplet. As already explained, O2 in the ground state is in the triplet state. It shows an exceptional behavior as the electronic transitions takes place from triplet ground state to triplet excited state. The type of transitions which certain categories of compounds undergo wavelength absorbed for these transitions are: saturated hydrocarbon or compounds containing carbon-carbon hydrogen single bond require very large energy to produce electronic excitation. Simple olefin has an absorption band at about 170 nanometer, and molecules like methylamine and methyl iodide, which do not contain pi orbital, undergo n to sigma star transition. All the electronic transitions in organic compounds do not occur in the ultraviolet region. The occurrence of compound indicate the absorption of radiation in the visible region, and compounds containing nitrogen double bond nitrogen group or long conjugated system including aromatic rings absorb at the wavelength greater than 180 nanometer. That is why they look colored. Such groups are called chromophores, and in such cases the energies of molecular orbitals lie close together and the pi to pi star transition takes place. Example, the protein beta carotene has a fairly long conjugated system at absorption at about 240 to 280 nanometer. Intensity of electronic bands. The intensity of any electronic band depend upon the extent of overlap between the wave functions of the ground state and the excited state. Greater the overlap, greater is the intensity. As there is a very poor overlap of the wave function in n to pi star transition and there is excellent overlap in pi to pi star transition, the intensity of the band produced by n to pi star transition is very low as compared to that produced by the pi to pi star transition. Further, in the presence of an acid, the electrons of n orbital undergo protonation and the n to pi star bands disappears. Thank you so much.